Welcome back to the deep dive. I am
Uh,
so glad you're here with us today because we're doing something a little bit,
a little different.
yeah, a little rebellious even. I mean, usually on this show, we take a topic and we drill down, we get microscopic.
We really do. We look at the tiny, tiny details of, history or technology or psychology.
Exactly. But today,
Uh.
we're doing the complete opposite. We are zooming out.
Way, way out. We're abandoning the microscope entirely.
We're leaving the atmosphere. We're leaving the ground. We are taking a tour, a massive visual, factual tour of the cosmos.
It's a bit of a terrifying prospect, isn't it, the cosmos? It sounds like we might be biting off more than we can chew.
It does, but we have a guide, a really good one, actually. We're working for the visual encyclopedia today, and specifically the sections on space, the solar system, stars, and galaxies. And the mission really is to take these incredible images, which you, our listener, obviously can't see right now, and translate them into audio. We want to paint the picture of the universe, starting right here in our own backyard, and then pushing all the way out to the edge of what's visible.
And what I really love about this source material is that it hammers home the idea of scale. I mean, it is so easy to look at a diagram in a textbook,
Oh, I know the one.
where the Earth and Jupiter are right next to each other and you think, okay, they're kind of comparable.
Yeah, one's a marble, one's a tennis ball.
Exactly. But the visual encyclopedia it drives home the sheer mind-breaking scale of reality. We're going to go from, the subatomic particle reactions happening inside the sun to something called the cosmic web, which creates these structures that are hundreds of millions of light years across.
It is a journey of extremes. I was looking through the notes, and we're going to talk about a magnetic bubble that protects our entire solar system.
The heliosphere, yeah.
Planets that might rain diamonds, or at least have these oceans of liquid metal, and cosmic lighthouses
Yeah.
that spin 700 times a second.
Pulsars. They're incredible.
Yeah. But, okay, before we get completely lost in the stars, I think we need to anchor this.
Good idea.
Why does this matter? I mean, why should you, listening to this, maybe you're driving to work or folding laundry, why should you care about the gas composition of Jupiter or the shape of some distant galaxy?
That is the big question, isn't it?
It is. And for me, I think it comes down to perspective.
Precisely. That's the word. Understanding our place in the cosmos, it shifts your perspective on literally everything. When you understand the ground you walk on, the sun that warms your face, the stars you might glance up at tonight.
Right.
When you realize that these aren't just, static background scenery, but they're these dynamic, violent, evolving engines, it changes how you see your daily life.
It connects you to a timeline that is so much bigger than your deadlines or your commute.
It really does.
Plus, we promise some genuine aha moments. I can guarantee that by the end of this deep dive,
Yeah.
you're going to know why you are literally made of star stuff.
And not in a poetic, metaphorical way.
No, I mean the actual hard physics of it.
Yeah.
You'll understand why the planets are arranged in the specific order they are, and what happens when two galaxies just decide to crash into each other.
It's a lot to cover. So, shall we start at the beginning? Or maybe start at home.
Let's start at home. The solar system. Now, I have to confess, when I was growing up, I had this placemat. You know the one I'm talking about.
Oh, absolutely. The yellow sun on the left, then all the little planets in a neat row.
A perfect straight row, evenly spaced, all about the size of a marble or a golf ball.
The classic, deeply misleading diagram. It's neat, it's tidy, and it is completely fundamentally wrong.
Exactly. It makes it all look so static, so permanent.
Yeah.
But the source material makes it really clear that the solar system is actually this chaotic, evolving beast. It wasn't always this way, and it won't always be this way.
And to understand why it looks the way it does today, we have to look at the baby pictures.
Baby pictures.
We have to rewind the clock about 4.6 billion years.
It's the casual stretch of time, 4.6 billion.
Well, in the grand scheme of the universe, our solar system is actually kind of middle-aged. But yeah, 4.6 billion years ago, there was no Earth, no sun, no Jupiter. There was just a solar nebula.
Okay, so paint the picture for us. What does a solar nebula actually look like? Are we talking about like a cloud in the sky?
It's a cloud, but on a scale that's it's impossible to really picture. We're talking light years across.
Light years. Trillions and trillions of miles.
Exactly. And it's mostly empty space, but it's got this this cold, dark mix of gas, mostly hydrogen and helium, sprinkled with these tiny little grains of heavier dust.
And this dust, this is the stuff that eventually becomes us.
That's the primordial stuff, yeah.
Hmm.
Leftovers from other older stars that lived and died, but at this stage, it's just cold and dark and very, very spread out.
So what's the trigger? How does it go from a cold, dark cloud to, well, the sun and everything else?
Gravity. Gravity is the architect.
Yeah.
But something has to give it a little push to get started.
A nudge.
A nudge. The leading theory is that a shock wave from a nearby supernova, another star exploding, rippled through this cloud.
Wow. So the death of one star is the trigger for the birth of another.
It's a cycle. That shock wave compresses a little pocket of this nebula just enough that its own gravity can take over. It begins to collapse inward under its own weight.
And as it collapses, I'm guessing it starts to heat up?
It heats up and it starts to spin, and as it spins, it flattens out.
I've heard this analogy before. It's like a pizza chef spinning dough, right?
It's exactly like spinning pizza dough. It's a physical principle called the conservation of angular momentum. A spinning sphere naturally flattens into a disk, so you end up with this spinning hot disk of material.
And most of it falls into the middle.
The vast majority. Gravity pulls about 99.8% of all that gas and dust into the very center. The pressure builds and builds and builds until it gets so hot, so dense that it ignites.
And that's our sun.
That becomes the proto-sun.
Okay, so the sun eats almost everything. It's a hungry center. But what about the crumbs? The little 0.2% left over?
This is where we get our first really big aha moment about the layout of our system. I mean, have you ever stopped to wonder why the rocky planets, Mercury, Venus, Earth, Mars, are all huddled up close to the sun,
Right.
while the big gas giants and ice giants are way, way out in the suburbs?
Honestly, I always just assumed it was random. Or maybe the bigger planets got thrown further out by centrifugal force or something. I don't know.
It is not random at all. It's a very specific sorting mechanism. The source calls it the frost line or the snow line.
The frost line. Okay, let's unpack that.
So think about the newborn sun. It's putting out a tremendous amount of heat, and it's also generating something called a solar wind.
Wind. In space.
Not like wind on Earth. It's a constant stream of charged particles blowing outwards from the sun at incredible speeds.
A cosmic leaf blower.
That's a perfect analogy. Now, in the inner solar system, close to that new star, it is way too hot for things like water, methane, or ammonia to stay frozen solid. They vaporize, they turn into gas.
And the cosmic leaf blower.
It blows them away. The solar wind pushes all those lighter, gassy materials out to the colder outer regions.
So close to the sun, the only things that can survive in solid form are the heavyweights, rocks and metals.
Exactly. Only the tough stuff, silicates, iron, nickel, could condense and clump together in that inner furnace. But here's the key. There wasn't a lot of that material to go around compared to all the gas and ice.
So the planets that formed there just didn't have much to build with. They stayed small.
Small, dense, and rocky. That's Mercury, Venus, Earth, and Mars.
But further out.
Further out, you get past this frost line, which is roughly located out in the asteroid belt between Mars and Jupiter, and suddenly it's cold enough for all those ices to freeze solid.
And there's way more ice than rock.
Oh, orders of magnitude more. So the planets that started forming out there had a massive advantage. They had so much more building material.
They hit the all-you-can-eat buffet.
They absolutely did. They grew huge really fast. They got so big, so massive, that their gravity became strong enough to grab onto and hold huge amounts of that primordial hydrogen and helium gas before the solar wind could blow it all away.
So Jupiter is a giant because it grew up in the part of the neighborhood where the fridge was always fully stocked.
That's a great way to put it. That sorting process, driven by the sun's heat and wind, defines the entire map of our system. It's why we have two very different kinds of planets.
That is fascinating.
Huh.
It explains the structure perfectly. But the map doesn't just end at Neptune, does it? This is something the source highlighted that I hadn't really thought about before, the heliosphere.
Yes.
The bubble.
Yeah, the bubble. We usually define the solar system by the orbits of the planets. But this is a bigger, sort of invisible definition.
It is. It changes the definition of solar system from a flat map to a three-dimensional territory.
So what is it?
Well, if you were an alien spacecraft approaching our system from deep space, the first thing you'd encounter wouldn't be Pluto or Neptune. It would be a boundary.
Oh, wall. More like a shock wave. Remember that solar wind we talked about?
The cosmic leaf blower.
That's the one. It's constantly blowing outward at supersonic speeds, past Earth, past Jupiter, past the Kuiper Belt. But interstellar space, the space between the stars, isn't completely empty.
There's stuff out there.
Right. The interstellar medium, it's very thin, but it has its own pressure. Eventually, the outward push of the solar wind gets weaker and weaker, and it runs up against the inward push of the interstellar medium.
And they meet.
They meet, and the solar wind basically slams on the brakes. It goes from supersonic to subsonic. That boundary is called the heliopause.
And that's the true edge of the sun's influence.
That is the border. Inside the heliopause, you are inside the heliosphere. You are inside the sun's protective magnetic bubble. Outside of it, you are in interstellar space.
And we've only sent 2 machines across that line in all of human history.
Voyager 1 and Voyager 2. They're out there right now, in the
Wow.
space between the stars.
It's like a force field. It defines our territory. It keeps most of the harsh interstellar radiation out and keeps our own solar atmosphere in.
That's a very good way to think about it.
Okay, let's zoom back in. Inside that force field, we need to talk about the boss, the powerhouse, the sun.
It is absolutely impossible to overstate how dominant the sun is. As I mentioned, it accounts for 99.8% of the total mass of the entire solar system.
99.8%.
Everything else. Jupiter, which is huge, Earth, all the asteroids, all the comets, you, me, your car, the oceans, we're all just the 0.2% of dust and debris floating around it.
We're the rounding error.
We are the rounding error.
It is mostly made of hydrogen, right?
About 70.6% hydrogen and 27.4% helium, yeah. But it's not what it's made of that matters so much as what it does with that hydrogen. It's not burning like a campfire. A campfire is a chemical reaction. The sun is a nuclear fusion engine.
We hear that term nuclear fusion a lot, especially with, clean energy news. But break it down for us. What is actually happening in the core of the sun?
It's a pressure cooker on a scale that is just unimaginable. The gravity is so intense that it's taking protons, which are just hydrogen nuclei, and forcing them together.
But protons are positively charged. They should repel each other, right? Like trying to push 2 north poles of a magnet together.
They absolutely do. They resist with incredible force. But in the core of the sun, the pressure is millions of times greater than on Earth, and the temperature is about 15 million degrees Celsius.
So it's enough to overcome that repulsion.
It overcomes the repulsion. They smash together and they fuse, eventually forming a helium nucleus. And here is the magic trick of physics.
Okay.
The resulting helium atom weighs slightly, just a tiny fraction less than the individual hydrogen protons that went in to make it.
Wait, so mass is lost. It just disappears.
It disappears as mass, yes.
Oh.
And where does that missing mass go? Well, Einstein gave us the answer. EMCO.
Energy equals mass times the speed of light squared.
That tiny little bit of missing mass is converted into a colossal amount of pure energy. Gamma rays, positrons, neutrinos, that's sunlight.
So the sun is literally evaporating its own mass into light and heat.
Billions of tons of it, every single second. It is slowly getting lighter just to keep us warm. But here's a fact from the source that absolutely blew my mind. The source calls it the slow burn, or the random walk.
Oh, I love this part. So fusion happens in the core. A photon of light is created. And you'd think, okay, light travels at the speed of light. It should just zoom right out of there instantly.
You would think so, but it doesn't. Not even close. The core of the sun is incredibly dense, about 150 times the density of water. It is a crowded dance floor.
Right.
A photon is created, it travels maybe a fraction of a millimeter, and smack, it slams into a charged particle. It gets absorbed, then it gets re-emitted. But it could go in any random direction.
So it's not a straight line. It's playing cosmic pinball.
That's a perfect description. It might bounce backwards, sideways, forwards. It does this millions and millions and millions of times. It is strictly a random walk, trying to find its way out of a maze.
And how long does it take? How long for that single packet of energy to get from the center of the sun to the surface so it can finally fly to Earth?
The estimates vary a bit, but the source notes it can take up to 100,000 years.
100,000 years.
Yeah.
That means the sunlight that's hitting your face right now was generated in the core of the sun when early humans were just figuring out stone tools and migrating out of Africa.
That's right. It's ancient light.
That is staggering.
Yeah.
It completely changes your idea of what sunlight is.
It does, but once it finally reaches the surface, the photosphere, the density drops, and it's finally free. From that point, it only takes about 8 minutes and 20 seconds to travel the 93 million miles to Earth.
Now, the sun isn't just a steady, boring light bulb.
Yeah.
The source talks about magnetic chaos. It sounds like a bad metal band, but it creates some pretty terrifying weather.
It does. The sun isn't a solid rock. It's a giant ball of gas and plasma. And because of that, it creates a phenomenon called differential rotation.
Okay, what's that?
It just means that the equator of the sun spins faster than the poles do.
So it doesn't rotate like a solid ball.
Exactly. And since the sun is highly magnetic, that uneven spinning does something pretty dramatic. Imagine you have a ball of yarn and you start winding it, but you're spinning the middle of the ball way faster than the ends.
The yarn would get all tangled up.
It would get twisted, knotted, and stretched. And that's exactly what happens to the sun's magnetic field lines.
And when they get knotted up really tightly, we see sunspots.
That's right. Sunspots are patches on the surface where the magnetic field is so knotted and intense that it actually stops hot gas from rising up from below. So that spot is cooler than the surrounding area, and it looks dark to us in comparison.
But the real drama happens when those twisted magnetic loops snap.
Like a rubber band
A
breaking.
really big rubber band.
A rubber band snapping with the force of millions of hydrogen bombs, that's a solar flare. Or, if it's a big enough event to actually launch material out into space, it's a coronal mass ejection.
And that's when it hurls billions of tons of plasma out into the solar system.
At 1,000,000 miles an hour.
And if that's aimed at Earth.
Well, if we're lucky, our magnetic field protects us, and we just get some beautiful auroras, the northern and southern lights.
And if we're unlucky.
If it's a really big one, like the famous Carrington event back in 1859, it can disrupt satellites, knock out power grids, and really mess with our communication systems. And this whole cycle of activity from quiet to chaotic and back, it follows a regular 11-year cycle.
The solar cycle.
The sun creates its own weather, and we live right in the path of the storm.
Okay, let's step away from the furnace before we get burned. Let's tour the rocky planets, the inner neighborhood. Mercury, Venus, Earth, Mars. We have to start with the little guy, Mercury.
Mercury is a planet of extremes. It's the smallest planet in the solar system. It's heavily, heavily cratered. It looks a lot like our moon at first glance.
But deep down, it's an anomaly.
It is. It has a massive iron core compared to its size. The core makes up about 85% of the planet's entire radius. It's almost all core with just a thin, rocky shell.
That's huge. Did it just forget to grow a mantle? What happened?
The prevailing theory is violence. We think Mercury probably started out much larger with a more normal rock-to-metal ratio. But early in the solar system's history, when things were much more chaotic and crowded, a massive protoplanet smashed into it.
A hit and run.
A cosmic hit and run, yeah. The collision was so powerful it blasted away most of the lighter outer rock, the mantle and the crust, and just left behind the dense iron core. It's essentially the stripped chassis of a much larger planet.
Wow. And the day versus the year situation on Mercury is also a total brain twister.
It is. Because it's so close to the sun's immense gravity has tidally locked its rotation in a very strange resonance. It spins very slowly on its axis, but it orbits the sun very fast.
And the result is bizarre.
The result is that a single day on Mercury from one sunrise to the next lasts 176 Earth days. But its year, the time it takes to go around the sun once, is only about 88 Earth days long.
So a day on Mercury is twice as long as its year. That would make scheduling meetings a complete nightmare. I'll see you next year, which is this afternoon.
Precisely. And because of that incredibly slow spin, the temperature swings are just brutal. It can get up to 430 degrees Celsius in the sun and then plummet to minus 180 degrees in the shade. It has no real atmosphere to distribute the heat.
Okay, let's move one planet out to Venus, Earth's evil twin.
A very, very apt name. If you just look at the specs, on paper, Venus seems like Earth's sister. It's almost the same size, almost the same mass, made of similar stuff. But somewhere along the line, something went very, very wrong.
The atmosphere.
The atmosphere. It's a profound cautionary tale. Venus has this super dense atmosphere, something like 96% carbon dioxide. The atmospheric pressure at the surface is more than 90 times that of Earth.
What would that feel like?
It's the equivalent of being a kilometer deep in the ocean. You'd be crushed instantly into a pancake. And all that CO2 has created a runaway greenhouse effect. The surface temperature is a steady 462 degrees Celsius, day and night, pole to pole.
Hot enough to melt lead.
Hotter than Mercury, even though it's nearly twice as far from the sun. The heat gets in, but it can't get out.
And the surface itself tells a violent story, too. The source mentions that Venus doesn't have tectonic plates like Earth does.
This is such a key difference. On Earth, Our crust is broken up into these plates that move around like puzzle pieces. This movement allows heat from the core to escape gradually through volcanoes, through mid-ocean ridges. It's like a pot of boiling water letting off steam.
And Venus is a sealed pot, a pressure cooker.
Exactly. The crust seems to be a single, solid, locked lid, so the heat from the core just builds up inside, and it traps and traps for hundreds of millions of years until the pressure becomes catastrophic.
And then what?
And then, the theory goes, the entire surface undergoes these massive, periodic, volcanic resurfacing events.
So instead of a few constant small volcanoes, you get a planet-wide apocalypse every few hundred million years.
That's the idea. It effectively melts its own face off just to release the pent-up heat.
Remind me never to visit. Let's get past Earth for a second. We live here. We know the Wi-Fi password. But I do want to touch on the moon for a moment. The source confirms the collision theory, right?
Yes, the giant impact hypothesis is the overwhelming consensus now. The idea is that a Mars-sized object, an object we've nicknamed Theia, slammed into the proto-Earth about 4.5 billion years ago.
And the moon is the debris from that crash.
The debris from both bodies was thrown into orbit, formed a ring, and then eventually coalesced under gravity to form the moon.
So the moon is technically part Earth and part invader.
Correct. And that collision was probably what knocked Earth onto its tilted axis, which is what gives us our seasons. It was a planet-defining moment.
Okay, and finally for the inner planets, Mars, the red planet. Let's start with the obvious question. Why is it red?
It's rust, literally. The surface is covered in fine iron oxide dust.
So it's a rusty planet. But it's not just a featureless dust ball. It has geological features that make Earth's look, well, tiny.
Oh, the scale on Mars is immense. Take Olympus Mons. It is a shield volcano, very similar in shape to the Hawaiian Islands, but it is 3 times the height of Mount Everest.
3 times.
Its base is about the size of France. If you were standing on the summit, you wouldn't even realize you were on a mountain because the slope is so gentle and it extends way beyond the horizon and practically reaches into space.
And what about the canyon? Valles Marineris.
It's a system of canyons that, if it were on Earth, would stretch from New York City all the way to Los Angeles. The Grand Canyon is a tiny little scratch compared to Valles Marineris.
And yet today, Mars is a cold, dry, seemingly dead world. Or mostly dead. We know it used to have water, right? We see the
We see ancient riverbeds, deltas, shorelines. We know liquid water flowed on the surface for a long time, but Mars has a fatal flaw. It's small.
Too small.
It's only about half the diameter of Earth. And because it's smaller, its internal core cooled down and solidified much faster than Earth's did.
And the core is what generates the planet's magnetic field.
Exactly. A liquid spinning iron core acts as a magnetic dynamo. When the Martian core cooled and stopped spinning, the dynamo shut down. The magnetic field died.
And without that magnetic shield.
The solar wind, that cosmic leaf blower again, was able to just strip the atmosphere away over millions of years. The air pressure dropped, the planet got cold, and the water either evaporated into space or froze solid underground.
It's a tragic story. A potential second Earth that just ran out of battery.
It really highlights how incredibly fragile and fortunate a habitable world like ours is. You need the right size, the right location, and a long-lasting magnetic engine.
Okay, we are crossing the frost line. We're heading out into the land of giants. Section 3, the outer giants. And we have to start with the king, Jupiter.
The scale of Jupiter is just, it's hard to get your head around. You could fit all the other planets in the solar system inside it and still have room to spare.
I think the number from the source was 1,300 Earths could fit inside Jupiter.
It dominates the solar system's gravity after the sun. It's the bouncer of the neighborhood.
And it's famous for those stripes. What are those?
Those are the zones and belts. They are basically high-speed jet streams moving in opposite directions. The light-colored zones are areas of rising gas, and the dark belts are areas of sinking gas. And the winds there are ferocious hundreds and hundreds of miles per hour.
And sitting right in the middle of all that is the Great Red Spot.
A gigantic anticyclonic storm that has been raging for at least 300 years, probably longer. It's shrinking a bit lately, but it is still big enough to swallow the Earth whole.
So what's inside Jupiter? We can't land on it, it's all gas. But deep, deep down, the source talks about liquid metal.
This is one of those physics extremes that I just love. Jupiter is mostly hydrogen gas, but as you go deeper, the immense gravity compresses that gas until it becomes a liquid.
Okay, liquid hydrogen.
But go deeper still, about 20,000 kilometers down, and the pressure becomes so incredibly intense that it actually squeezes the electrons right off the hydrogen atoms.
So the atoms break apart.
The electrons become detached and can flow freely, just like they do in a metal. It becomes liquid metallic hydrogen, and this creates a vast, churning ocean of conductive fluid deep inside the planet. And it's this spinning ocean of metal that generates Jupiter's unbelievably powerful magnetic field, which is by far the strongest in the solar system. It's a dynamo on steroids.
Let's move next door to Saturn.
Yeah.
The jewel of the solar system. Obviously, we have to talk about the rings.
They are the most spectacular sight in the system, no question. But they are surprisingly thin. I mean, they're hundreds of thousands of kilometers wide, but in most places, they're only about 10 meters thick.
As thin as a two-story building.
Yeah. If you made a scale model of them with a sheet of paper, the paper would be too thick.
And they're not solid, right? They're made of individual particles.
Trillions of them, mostly water ice. And they range in size from tiny specks of dust to boulders the size of a house.
So why does Saturn have these incredible rings and, Earth doesn't?
The leading theory is a destroyed moon. That a moon, or maybe a large comet, got too close to Saturn. It passed something called the Roche limit.
The Roche limit.
It's the distance from a planet where the planet's tidal forces, its gravity, are stronger than the moon's own gravity holding it together. Saturn's gravity literally tore the moon apart and spread the debris into the beautiful ring system we see today.
So they're the glittering remains of a cosmic tragedy.
You could say that.
And the planet itself, it has that funny density fact.
It does. Saturn is massive, but it's very fluffy. It has the lowest average density of any planet in the solar system. It is actually less dense than water.
So the classic line is,
if you could find a bathtub big enough, a truly galactic-sized bathtub, Saturn would float.
I love that visual. Now let's keep going out to the dark, cold edges of the planetary system. Uranus and Neptune. They're often lumped together with Jupiter and Saturn as gas giants, but the source makes a point to correct that. They're ice giants.
And that distinction really matters. Jupiter and Saturn are almost entirely hydrogen and helium gas all the way down. Uranus and Neptune have hydrogen and helium atmospheres too, but their interiors, their mantles, are mostly made of ices.
And in astronomy, ice doesn't just mean frozen water, does it?
No. It's shorthand for a mix of water, ammonia, and methane. These heavier compounds make up a much larger fraction of their total mass.
And that different chemistry changes how they look.
It absolutely does. The methane gas in their atmospheres is very good at absorbing red light. So when sunlight hits these planets, the red part of the spectrum gets absorbed, and the blue and green light gets reflected back at us.
Which is why Uranus is that pale, hazy cyan color, and Neptune is that deep, brilliant azure blue.
Exactly. It's all about the methane.
Uranus is the weird one of the family, though, the sideways planet.
It is truly baffling. Every other planet in the solar system spins more or less like a top, relatively upright as it goes around the sun. Uranus effectively rolls on its side. Its axis is tilted by 98 degrees.
98 degrees, so it's basically lying down.
For part of its orbit, its north pole points almost directly at the sun. It leads to the most extreme seasons imaginable.
How does something like that even happen?
Again, the answer is probably violence. The best theory is that a massive collision with an Earth-sized object billions of years ago literally knocked it completely over onto its side.
And what about Neptune? It's the windy one.
The windiest, supersonic winds, the fastest in the entire solar system, reaching speeds of over 2,000 kilometers per hour. And interestingly, Neptune has a strong internal heat source. It radiates more heat into space than it receives from the distant sun.
And that internal heat is what drives the crazy weather.
It churns the atmosphere and fuels those incredible winds. Uranus, by contrast, lacks that internal heat, which is why its atmosphere looks much calmer and hazier.
Okay, we have done the grand tour of the planets, but the solar system is full of so much other stuff. Section 4, the leftovers, asteroids, comets, and dwarf planets.
Leftovers is a bit dismissive, but it's also very accurate. These are the building blocks that never quite managed to come together to form a full-fledged planet. They're like time capsules from the original solar nebula.
Let's start with the asteroids. They're mostly in that belt between Mars and Jupiter. But the source mentions something called Trojan asteroids. I'm assuming they aren't hiding inside a giant wooden horse.
No, not quite. The Trojan asteroids are fascinating. They're trapped in Jupiter's immense gravity well. But they're not orbiting around Jupiter. They actually share Jupiter's orbit around the sun.
How is that possible? How do they not crash?
They sit in these special stable points in space called Lagrange points. These are spots where the gravity of the sun and the gravity of Jupiter perfectly balance out. One camp of asteroids is trapped 60 degrees ahead of Jupiter in its orbit, and the other is trapped 60 degrees behind it.
And they're named after the Trojan War.
Yes, they're named after the heroes from the Iliad. The camp ahead of Jupiter is the Greek camp, and the one behind is the Trojan camp.
That is surprisingly poetic for a bunch of space rocks.
It is. And asteroids aren't all the same. The source breaks them down by their composition. You have C-types, which are carbon-rich and dark like coal. You have S-types, which are stony. And then you have M-types, which are metallic.
Pure metal.
Basically chunks of pure iron and nickel. They're thought to be the shattered cores of protoplanets that were destroyed in collisions long ago.
Okay, let's go even further out, past Neptune. We get to the Kuiper Belt. This is Pluto's neighborhood.
The Kuiper Belt is this huge, donut-shaped region of icy bodies that surrounds the main solar system. This is the native home of the dwarf planets.
All right, can we briefly get into the definition of dwarf planet? I know people are still salty about Pluto getting demoted.
It's a purely orbital definition, and it's pretty clear-cut. The International Astronomical Union says that to be a planet, an object must do three things.
Okay.
1, it has to orbit the sun. Pluto does that. 2, it has to be spherical. It needs enough gravity to pull itself into a round shape. Pluto does that too.
So what's the third one?
It has to have cleared its orbit.
And what does that mean?
It means it has to be the gravitational bully of its neighborhood. A major planet like Earth has either absorbed or ejected all the other debris in its orbital path. Its orbit is clean.
And Pluto.
Pluto has spectacularly failed to do this. It sits right in the middle of the Kuiper Belt, surrounded by thousands and thousands of other icy objects. It hasn't cleared anything. It's just one prominent member of a very large crowd.
Who else is in that crowd?
Oh, there's Eris, which is actually more massive than Pluto. There's Haumea, which spins so fast it's been stretched into the shape of a football. There's Makemake, the busy neighborhood out there.
The source also highlights a specific object out there called Aerokoth. It has a really funny shape.
The snowman.
Literally.
Visually, yes. It was visited by the New Horizons probe after it flew past Pluto, and it looks exactly like two reddish snowballs that have been gently pressed together.
And that tells us something important.
It tells us how planets form. It clearly wasn't a violent crash. These two objects must have been orbiting each other very slowly and then just gently drifted together and stuck. It's a contact binary. It's a pristine relic from the very dawn of the solar system.
Okay, finally for the leftovers, we have the comets, the icy visitors.
Comets are the long-range travelers. They don't come from the Kuiper Belt. They come from a much more distant place called the Oort cloud.
The Oort cloud.
It's a theoretical thick bubble of trillions of icy bodies that surrounds our entire solar system, maybe up to a light year away from the sun.
And sometimes one of them gets knocked loose and falls inwards.
Exactly. And as this dirty snowball gets closer to the sun, it starts to warm up. The ice on its surface doesn't melt, it turns directly into gas, a process called sublimation.
And that's what creates the famous tail.
It creates the coma, which is the glowing cloud of gas right around the nucleus, and it creates the tails, plural.
Plural. Tails. I never realized there were two.
If you look closely at a good photograph of a comet, you can usually see them. There's a bright white or yellowish curved tail. That's the dust tail. It's made of heavier particles that are trailing behind the comet in its orbit.
Okay.
But there's often also a fainter, straighter, bluish tail. That is the gas tail or the ion tail.
And why is that one straight?
The solar wind again. The solar wind is made of charged particles, and it pushes the charged gas from the comet directly away from the sun, regardless of which way the comet is moving. It acts like a windsock in space.
So if a comet is moving away from the sun, its gas tail is actually out in front of it.
Exactly. It doesn't trail behind the comet's movement. It points directly away from the sun.
That is so counterintuitive.
Yeah.
I love it. Okay, we have toured the neighborhood. Now we need to look at the lights themselves. Section 5, the life and death of stars.
We're really stepping up in scale and energy now. Stars aren't eternal. They're born, they live, and they die, and it's in their death that they give life to the rest of the universe.
Let's start with birth. We're back to nebulae.
Huge clouds of gas and dust. We call them stellar nurseries. The Orion Nebula is a famous one you can see with binoculars. Inside these vast clouds, Gravity causes dense little knots of gas to collapse in on themselves.
And as they collapse, friction heats them up.
They get hotter and denser, forming a protostar, and when the core gets hot enough, about 10 million degrees Celsius,
Ignition.
hydrogen fusion begins. A star is born.
And they come in this rainbow of colors. But the source points out something that trips a lot of people up. The color scale in astronomy is the complete opposite of the taps in my bathroom.
It really is. We associate red with hot and blue with cold. But in the physics of light, blue is hot, red is cool.
Why is that?
Think of a flame on a gas stove. The blue part at the base of the flame is the hottest part. It's the same with stars. A Class O blue star is scorching hot, burning at over 30,000 degrees Celsius on its surface.
While a red star.
A Class M red star like Betelgeuse in Orion is relatively cool, at only around 3,000 degrees.
Cool, being a very relative term here.
Very relative.
Now, most stars we see are in what's called the main sequence. That's like the prime of their life, right?
That's right. A star will spend about 90% of its entire life on the main sequence. It's a period of stability. It's a perfect balancing act.
A balancing act between...
Gravity is constantly trying to crush the star inward, but the energy from the nuclear fusion in the core is creating an outward pressure. For billions of years, those two forces are in perfect balance. It's called hydrostatic equilibrium.
But eventually, the fuel starts to run out. And this is where the story branches. The destiny of a star depends entirely on its size.
Size is destiny. Let's start with a low-mass star, like our sun.
Okay, what is our sun's fate?
We burn slow and steady. The sun has about another 5 billion years of fuel left in the tank. But when the hydrogen in the core finally runs out, that balancing act fails. The core will start to collapse under its own gravity.
And a collapse heats it up again.
It heats it up enough to start burning the next element available, helium. The outer layers of the sun will then expand massively. The sun will swell up into a red giant.
How big?
It will grow large enough to completely swallow Mercury and Venus. It might stop just short of Earth's orbit, or it might consume us too. Either way, the surface of the Earth will be vaporized. It's toast.
So, not good. And then what?
For a star like the sun, it can't get hot enough to fuse anything heavier than carbon and oxygen. So after the helium runs out, the engine in the core dies for good. It gently puffs off its outer layers into space.
And that creates a planetary nebula.
A beautiful, glowing shell of gas, yes.
Yeah.
Which is a terribly confusing name because it has nothing at all to do with planets.
Blame the old-timey astronomers with their weak telescopes.
Exactly. And in the center, all that remains is the dead core. A white dwarf.
What's a white dwarf?
It's a ball of super dense carbon and oxygen, about the size of the Earth, but containing the mass of the sun. It's incredibly dense.
And it just sits there and glows.
It's a cosmic ember. It's no longer generating new heat, but it glows white hot from all the leftover heat. And over trillions of years, it will slowly cool down and fade away.
Eventually becoming what's called a black dwarf.
Correct. A cold, dark, dead star floating in space. But here's a truly haunting fact. The universe is about 13.8 billion years old. It takes longer than the current age of the universe for a white dwarf to cool down completely.
So, wait, does that mean there are no black dwarfs yet? Anywhere?
None. The universe is too young. Every single white dwarf that has ever been created is still out there glowing somewhere. We are still living in the bright, early era of the universe.
That is comforting.
Yeah.
In a very weird way.
Mm-hmm.
Okay, so that's the story for low-mass stars. What about the big boys, the high-mass stars?
They live fast and die young. They burn through their fuel in just millions of years, not billions. They swell up into enormous supergiants. And because they're so massive, their cores get much hotter. They can fuse heavier and heavier elements.
Go past helium?
They fuse helium into carbon, then carbon into neon, then oxygen, then silicon. It's like an onion, with layers of different elements being fused. They're building the periodic table in their core.
Until they hit iron. The source says iron is the kiss of death for a massive star. Why iron?
Because of a quirk of nuclear physics. Fusing elements that are lighter than iron creates energy. It releases energy that pushes outwards and holds the star up. But trying to fuse iron consumes energy. It takes more energy than it releases.
So the moment the core starts making iron, the engine stalls.
The furnace goes out, the outward radiation pressure stops instantly, and gravity wins. Catastrophically.
Collapse.
The core collapses from the size of the Earth to the size of a city in less than a second. It hits the maximum possible density and then rebounds. That rebound creates a shockwave that blows the rest of the star completely apart. That is a supernova.
The biggest explosion in the universe.
For a few weeks, a single supernova can outshine an entire galaxy of billions of stars. It's an unbelievably violent event.
And what's left behind is even crazier than a white dwarf.
If the star was big, but not too big, you get a neutron star. The collapse is so intense it crushes protons and electrons together to form neutrons. You're left with a ball of pure neutrons the size of Manhattan.
But with the mass of the sun.
Or more. The density is just absurd. A single teaspoon of neutron star material would weigh about 3 billion tons on Earth. It is essentially one giant atomic nucleus.
And some of them spin really, really fast.
That's a pulsar. It's the figure skater effect again. When the huge star shrinks down to the size of a city, it spins up incredibly fast. Some of them spin up to 700 times a second.
700.
And they have intense magnetic fields that funnel beams of radiation out from their poles. As the star spins, that beam sweeps across space. If it happens to sweep past Earth, we detect a regular pulse of radiation. Blip, blip, blip. They are the most precise clocks in the universe.
Okay, but what if the star was really, really massive to begin with?
Then even the neutrons can't stop the collapse. Gravity wins completely and totally. The core collapses all the way down to a single point of infinite density. A singularity. It creates a black hole.
The point of no return.
Literally. It creates a boundary around it called the event horizon. That is the boundary where the gravity is so strong that the escape velocity exceeds the speed of light. And since nothing in the universe can travel faster than light, nothing can ever escape. Not a spaceship, not a planet, not even light itself. It is a hole in the fabric of reality.
The ultimate cosmic trap. Okay, we have stars, we have their dead remains. Now let's zoom out again to the biggest structures of all. Section 6. Galaxies and the large-scale structure.
Galaxies are cities of stars, huge collections of millions or billions or even trillions of stars, all bound together by gravity and a lot of dark matter. Our home city is the Milky Way.
What kind of city is it? What does it look like?
It's a barred spiral galaxy, so it looks like a beautiful pinwheel, but with a straight rectangular bar of stars across the very center. It's huge, about 100,000 light years from one side to the other.
And where are we? Are we living downtown?
No, we're out in the quiet suburbs. We're in a minor spiral arm called the Orion Spur, which is tucked between the two much larger Perseus and Sagittarius arms. We're about 26,000 light years away from the galactic center.
Which is probably a good thing.
A very good thing. Downtown is a dangerous place. There's much more radiation, stars are packed much more closely together, and right at the very center, the bullseye, sits Sagittarius A star, our very own supermassive black hole.
How massive?
It has the mass of 4 million suns.
4 million, wow. But not all galaxies look like our pinwheel. The source brings up the tuning fork diagram.
Ah, yes, Edwin Hubble's classification system. It's a way he sorted galaxies by their shape. On one side, you have ellipticals, which look like fuzzy, featureless rugby balls or spheres. They're usually massive, but kind of boring. They're mostly full of old, red stars, and they don't have much gas left to make new ones.
On the other side, you have spirals like us.
Right, flattened disks with those beautiful spiral arms, and the arms always appear brighter and bluer. That's because the arms are density waves. They're like cosmic traffic jams of gas and dust. That compression triggers new star formation. So the arms are where all the young, hot, brilliant blue stars are being born.
And what about the ones that don't fit? The messy ones.
Those are irregular galaxies. They're small, chaotic blobs with no defined structure, and they're often shaped that way because of collisions with other galaxies.
That brings us to interactions. Galaxies look so serene and static, hanging in the blackness. But they dance. They collide.
They absolutely do. Gravity pulls them together over billions of years. The source has a famous image of the antenna galaxies. It is a stunning snapshot of a car crash in super slow motion. It's two spiral galaxies in the process of colliding.
So what actually happens when they crash? Do the stars all smash into each other?
You'd think so, but surprisingly no. The space between individual stars is so incredibly vast that when two galaxies collide, the stars themselves almost all just pass right through each other like ghosts. It's extremely, extremely unlikely for two stars to actually hit head-on.
So where's the violence? Where's the action?
The gas clouds. The huge nebulae, they can't pass through each other, they slam into each other and compress. That compression triggers a massive galaxy-wide burst of new star formation. We call it a starburst. And the immense tidal forces of gravity tear long streams of stars and gas out into space, creating these long tails. That's why they're called the antenna galaxies.
And eventually, the two galaxies merge into one big, messy blob.
Yes. Over hundreds of millions of years, they settle down and usually form one giant elliptical galaxy. And this is actually the fate of our own Milky Way.
What?
We are on a direct collision course with our nearest big neighbor, the Andromeda Galaxy.
You're kidding. When does that do?
In about 4.5 billion years. So, mark your calendar.
Okay. And if we zoom out to the absolute maximum possible scale, even past the galaxies, the source calls it the cosmic web.
This is the largest scale of reality that we know of. If you map the location of millions and millions of galaxies, you find they are not scattered randomly like salt on a table. They form a structure,
A pattern.
a distinct pattern. They cluster together in long, thin filaments and broad, flat sheets, and these structures surround huge, almost empty bubbles called voids.
It looks like a sponge or a neural network in a brain.
It really does. It's this beautiful, intricate web of light stretched across the vast darkness of the cosmos.
From the dust on the moon to the web of the entire universe, we have covered some serious ground today.
They certainly have.
So let's try to wrap this all up. We started with the question, why does this matter? And we promised to explain why you, the listener, are literally made of star stuff.
It all comes back to that stellar life cycle we talked about. Remember, the universe started out with only hydrogen and helium and a tiny bit of lithium. That's it.
That's pretty boring stuff. You can't build a human or a rock or a smartphone out of just gas.
Exactly. You need the heavier elements. You need carbon, nitrogen, oxygen, iron.
So where did they come from? They didn't exist after the Big Bang.
They had to be manufactured. They were forged in the high-pressure cores of stars, crushed together by gravity. And the only reason those elements are here on Earth, in your blood, and in your bones is because those stars died.
Supernovae.
Supernovae. When those massive stars exploded, they blasted all those heavy elements they had created out into the galaxy. They enriched the interstellar gas clouds. So when our own solar nebula collapsed to form the sun and the Earth, it was seeded, it was salted with the ashes of countless dead stars.
So we are literally the recycled nuclear waste of ancient stars.
I prefer to say stardust, but yes, nuclear waste is technically accurate. Every single atom of iron in your blood was once inside the core of a star that violently exploded billions of years ago.
That connects us to the cosmos in a very real, very physical way. And I want to leave everyone with that thought you mentioned earlier about the black dwarf.
Yes.
You say the universe isn't old enough for a single star to have completely cooled down and gone dark yet? It just reminds me that, cosmically speaking, the party is just getting started.
We are in what astronomers call the stelliferous era, the era of the stars. The lights are on, it's bright, it's energetic, but it won't last forever.
What happens next?
Billions, and then trillions of years from now, the gas will run out, star formation will slow down, and then stop. The lights will go out one by one, the universe will get darker and colder and much, much quieter.
So enjoy the view while it lasts.
Exactly. We are incredibly lucky to be here right now to see it all.
So the next time you walk outside on a clear night, look up. You're not just looking at pretty little lights. You're looking at nuclear engines. You're looking at colliding galaxies. And you're looking at the ancient history of the very atoms in your own body. You have the decoder ring now. Use it.
All said.
Thanks for diving deep with us. We'll see you on the next one.
Goodbye, everyone.